Now that we have the formalities out of the way, I wanted to talk a little bit about evaluating scientific claims, what Carl Sagan called the Baloney detection kit. Now, we are going to be evaluating lots of scientific claims in this class and some unscientific claims in this class, and we have to be able to evaluate what is a valid scientific claim and what's an invalid scientific claim. So I wanted to give you these tools right away so you can put them aside and use them whenever we're talking about any scientific idea or unscientific idea that comes across in this class. We're going to be talking about some crazy stuff: origin of the universe, exploding stars, black holes, dark matter, dark energy, special relativity, time dilation, things that are going to blow your mind. And you need to be able to evaluate whether what I'm going to be presenting to you is baloney or not. Okay, so where did the kit come from? For those of you who don't remember Carl Sagan, he was a fantastic scientist and an educator who died relatively young in 1996 from cancer. But he was a proponent of the idea that every citizen, every person in the world should have some ability to navigate a scientific society. And he wrote a book called The Demon-Haunted World, which was an exploration about how we've used science to get out, to kind of crawl out of the darkness of our own ignorance to understand and be able to explore the universe. And so in that book, he noted something called the Baloney detection kit, a bunch of tools that allow you to figure out whether or not something is baloney or not, be able to evaluate whether or not a claim being made is a scientifically valid claim or whether it's total nonsense. It's not so concerned with figuring out whether or not an argument is correct or not. It's tools to evaluate whether an argument is valid. And those are kind of two different things, because I can make a very valid argument for something that's incorrect, but I'm doing it in good faith. I may be wrong. However, there are people out there who make arguments specifically to deceive or to manipulate. And so it's important to be able to tell what's going on there. And the reason I'm bringing this up first is because in this class we'll be looking at a bunch of information online, reading articles in your textbook, and we want to be able to have a way to evaluate all of this information that comes at us. Okay, so number one of the baloney detection kit is to get the facts. Wherever possible, there must be independent confirmation. This can be a challenge in science. It's sometimes not challenging in life. If somebody tells you there's a car wreck and you can go outside and witness the car wreck, you'll see that it actually happened and you get the facts. But in science, we do experiments and we observe things, and corroborating those yourselves when you're not an expert in a particular field can be difficult. And so what we look for is not just one group of people or one researcher who has discovered something, as we look for a number of people who have independently verified that. So even if you feel like you aren't competent to go off and do a particular experiment yourself, and frankly most of us aren't, even those of us who do science are not competent to do experiments in other fields, we can still evaluate the claim by seeing whether or not it's corroborated by other groups doing similar experiments. Once you have the facts, you want to encourage debate. Substantive debate. This means debate about what are the possible ideas and about what is going on. And we are particularly interested in knowledgeable debate. It'd be nice if we could find knowledgeable people to debate the particular ideas that we can interpret with those facts. And knowledgeable is important. You know, if you want to do a discussion of global climate change, you don't bring in a specialist in, I don't know, computer design, right? I mean, you want to talk to people who specialize in that area. So we want to look for substantive, knowledgeable debate, but bring in all points of view. We just want to make sure that people are debating with some knowledge behind that. But at the same time, when we bring in knowledgeable people, we aren't allowed to do any name dropping. And this can be as simple as, you know, my research advisor says that the canyons carved on Mars were carved by wind instead of water, and that's not a good argument, because I'm just appealing to the authority of my research advisor. I'm not bringing any new substantial information to the debate. The ultimate appeal to authority that we can never do in science is to say that God did it. Ever. Scientists just aren't allowed to do that. And the reason for that is because when do you draw the line? You know, do I say God carved the canyons on Mars? Do I say God created the origin of the universe in the Big Bang? Do I say God created the galaxies and then everything else happened from that? There's no, that's like the ultimate name dropping. You say because God did it. And regardless of whether that's true or not allowed to say that. So we leave the name dropping out. We also have to have a lot of ideas, and this is particularly hard for scientists because we come up with an idea and we love our new ideas, and oftentimes we get rewarded for having excellent new ideas, say for the Nobel Prize. And so if you have a really great idea, sometimes you can fall into promoting it because it was the first idea you had. That's not necessarily the best thing to do. You want to try and spin a bunch of ideas and kind of see which one shakes out. We also want to make sure that we're not just listening to ideas because there are ideas. We want to make sure that we listen to everybody. This is also a challenge for scientists because it's more fun when the idea that's right is our idea. And sometimes we don't want to listen to other people because they might be right and I might be wrong. And that's just a human thing. We don't like to be criticized. We don't like to be wrong. But too bad. We have to listen to others. And it's good to keep that in mind when you're having a debate or an argument with somebody, is to listen to what everybody has to say, because good ideas can come from pretty much anywhere. The next thing is to make sure we quantify our discussions when we're talking about a scientific claim. If I tell you the universe had a beginning, that is a valid scientific claim, but it's not terribly useful. If I tell you that the universe began 13.7 billion years ago, plus or minus 0.1 billion years, that is a pretty compelling, at least it compels me to want to go look into that idea further because I'm giving you a very specific quantitative result, so therefore I must have some observations or facts to back that up. At least one would think. Now we have to be a little bit careful because oftentimes people will use numbers to deceive. And they will quantify things sometimes that are unquantifiable, or they'll just make stuff up, and so you have to make sure that you know where those numbers came from. But all other things being equal, a quantifiable argument is a better argument than one that can't quantify things. Once we quantify things, we have a chain of reasoning that leads us from the beginning of our hypothesis to argue all the way to the end of our conclusions, and every single chain of that reasoning must hold true. One of the most important tools for evaluating a scientific claim is something known as Occam's razor, and that is simply a way of deciding if we have two equally valid or at least equally plausible ideas. We take the simplest one just as a matter of course. A perfect example of this is the argument for a heliocentric or sun-centered solar system versus a geocentric or earth-centered solar system. Both more or less match the observations of the motions of the planets, but as we'll find out, the geocentric model is much more complex than the heliocentric model. And so even though the heliocentric model kind of goes against our gut feeling that we're just sitting here stationary on the Earth, it's important to notice that, well, it's the simplest model that fits all the facts. Okay, a hypothesis is only scientifically verifiable if it is falsifiable. Now this is contrary to a lot of what people understand about science, is that scientists doesn't prove anything. Scientists can't prove anything. What we can do is we can prove things wrong. We can falsify claims. So if I have a claim that the universe is 13.7 billion years old, I can't prove that that's correct. I can only do experiments and see if they validate that result. If I come up with an experiment that finds out that the universe is actually 15 billion years old, I've proved my original hypothesis incorrect. And so we can prove things wrong, but we can't prove things right. And so we have to make sure things are falsifiable. So when you listen to somebody's argument, one of the best ways to tell if it's a scientific argument or a scientific claim is to see if it's falsifiable. If you can imagine an experiment that would falsify the claim, then we consider it a falsifiable scientific claim. A great example of this is a colleague of mine has the idea that there could be little microbes living in the clouds in Venus's atmosphere, the planet Venus. That sounds like a crazy idea, but you can imagine flying a spacecraft to Venus, swooping through the clouds, picking up samples of the clouds and culturing them for organisms. And so it is a falsifiable claim. So it is a scientifically valid hypothesis. Speaking of experiments, that is one of the things that sets science apart from almost every other way of exploring the world and exploring the universe, is that we rely on experiment and observations to validate or falsify our claims. We do experiments all of the time. We're very careful about the way we design experiments. In astronomy, less experimental, more observational science, where we observe things in the universe and try to observe many things in the universe over and over and over again to see if we can figure out what's going on. Everything we do in this class, we will tie back to observation in some way. And if we can't tie it back to observation, we won't consider it a scientific claim. All right, once you've got a valid hypothesis and a scientific argument, you still have to be careful of logical pitfalls, because when I'm arguing the case, I want to make sure that I don't basically falsify my own argument by arguing incorrectly. And by incorrectly, I mean there are things that you can do in an argument which makes it so that your argument is no longer valid. And one of the clear ones is something called ad hominem, which means that I attack you with my argument. I can say that what I'm saying is correct because you're an idiot. I mean, just insult somebody. That is not a particularly good argument strategy, although people do that all the time. If you just watch some of the Fox News and CNN, you'll see this happen all the time. But if you go to yourlogicalfallacies.com, you can see a description of all of these different types of logical fallacies. Some that you might be aware of are things like argument from adverse consequences. I'm correct because if you don't believe me, something really horrible is going to happen. Take a moment to go to yourlogicalfallacies.com and look at these and see if you can't point these things out, either when you're discussing things with other students in the class or with your friends, or even me. I often make mistakes and make logical pitfalls when I'm trying to explain a particular line of reasoning. And lastly, I added this one myself. It's called Follow the Money, and the reason I put this one in there is oftentimes you can evaluate the validity of a claim by just looking to see who funded it. To give you an example, there's a website called co2isgreen.org, and the principal argument of this website is that CO2 is nothing but beneficial to the environment and has absolutely no impact on global warming or global climate change. That is a falsifiable argument, but if you look at who funds that website, you'll find that it's a coal PR firm, and so it makes you question whether or not that's an accurate claim just based on who's funding it. Now, it could very well, it doesn't mean it's not an inaccurate claim. You still have to go check and see what data backs up their claim, but you can kind of get a feeling by going to the source and seeing who paid for it to see whether or not a claim is valid or not. All right, so that's the baloney detection kit. We'll be using that throughout the course. Next up in our video series is going to be a discussion of the scales of the universe, and we'll see if we can blow your mind.